In this lecture, I want to cover several useful techniques that will simplify op-amp circuit analysis. In total, I have 7 of them, I think, and so we'll jump right into it. The first one is to remember the Thevenin equivalent input and output circuit of the op-amp. This addresses the question of how do I include an op-amp in this larger circuit that I'm now trying to solve. And the way you want to think of it is an ideal controlled voltage source putting out a voltage AV times delta V, where delta V is the voltage between V minus and V plus. And there is no input resistance, so we'll say Rn is equal to infinity, and there is no output resistance. That means when you connect an op-amp, or let's say I have this following circuit here. Let's do a simple inverting op-amp. Okay, R2, R1, VI, and here's VO. And let's say you have a circuit where you see a R3. Okay, the thing to remember is that because the op-amp has a zero output resistance, loading the output, in other words, adding a resistance over here, R load, which in the circuit below is R3, has no impact on the output voltage VO. If RO right here was something other than 0, right, then you would have voltage division. But this, you can replace this. Okay, so I'll say to solve for VO, remove or ignore R3. So we can go back and draw our circuit without R3. Of course, it's simply minus R2 over R1 VI. So don't let some impedance, whether it's resistance, a capacitor, an inductor, hanging at the output affect or cause you to think that the output voltage will be affected. Here's another example. If I had some op-amp and now I had this connected to, say, some voltage, right, 5 volts, and you ask for VO. Well, VO is not a function of R5 or 5 volts. Why? Because again, what's inside here is a voltage source. The voltage source trumps the voltage across its terminals. It's going to determine what the voltage is across its terminals. And so R3 and 5 volts will not matter. Similarly, on the input side, if we have a voltage divider, say, right here, and I'm going into either input, but let's say the positive input, to find this voltage V plus, I can ignore the op-amp. Why? Because there's zero current flowing into the input terminal. So to find V plus, ignore the op-amp. So we'll just redraw this. Call this V plus. We have VI, R1, and R2. And V plus is nothing more than just voltage divided version of VI. Okay, the second item is use superposition or KCL at the inverting input. use superposition or KCL at the inverting input V minus. And we'll look at a couple cases here. So suppose we have, again, this, I'll draw the inverting op-amp topology. Okay, and we're looking for VO. And we'll say, in this case, let's just say this is V plus is at V2 here. Find VO. In this case, I would recommend to use superposition at V minus. So you redraw this. You have VO here, you have V minus, and we have VI. And we can say V minus is equal to R2 over R1 plus R2 VI plus R1 over R1 plus R2 times VO. And in this case, because well, V minus is equal to V plus, but V plus is equal to V2, we then can solve for VO. And what would we have? We would have R1 plus R2 over R1 V2 minus R2 over R1 VI. So here we've used superposition. Now we can use, let's say that we have another slightly different circuit. So I have several sources, V1, V2, V3. Call this RF, say R1, R2, R3, and we'll call this VX here. Okay, and let's say this is equal to 0. Vx is equal to 0, so the non-inverting is grounded. We're looking for VO. I would say in this case, use KCL at V minus. So we look at this node here, and we see that we have 3 current paths through R1, R2, R3, and then a 4th current path through RF, right? This goes in to the same node. There's no current path into the op-amp. So we have 4 sources of current, and we could write the following: V1 minus V minus, right, which is equal to V plus, which is equal to Vx, which in this case is 0, right, over R1, plus V2 minus, would be the same thing, I'll put 0 though in this case, minus 0 over R2 plus V3 over R3 plus VO over RF is equal to 0. Okay, this will lead you to a much simpler solution. In fact, you can see immediately that VO is equal to minus, what is it, minus RF over R1 V1 plus RF over R2 V2 plus RF over R3 V3. Very simple to arrive at that, right? We could have used, okay, I'll say don't, use superposition in this case. I'll see if we try to use superposition, we'd say VO is equal to RF in parallel with R2 in parallel with R3 divided by R1 plus that same parallel mess times V1 plus, now we go RF in parallel with R2 in parallel with R3 over that same parallel mess plus R2 V2, and you see where this is going. It's just messy. RF in parallel with R2 in parallel with R3 over that same parallel combination plus R3 V3. You can get to the right answer this way, but look at how much work it involves, right? Much easier in this case to just sum the currents into that V minus node as opposed to doing superposition. Now what if we had this same case where we had the three resistors summing in to the inverting input, but now we had the non-inverting input equal to, let's say, 2 volts, right? How would we solve in this case? Well, we would say, we could still do KCL, still better than superposition. We would say V1 minus 2 volts over R1 plus V2 minus 2 volts over R2 plus V3 minus 2 volts over R3 plus VO minus 2 volts over RF is equal to 0. And you could solve for VO in that case, which will be of the form VO is going to be VO will still have the form that we saw before, minus RF over R1 V1 plus RF over R2 V2 plus RF over R3 V3, but then there will be another term that will be due to the 2 volts. This is one way to solve this. Now this leads me to the next point. So we'll kind of leave this problem open, and we'll resolve it here momentarily. So the next one is use superposition when there are independent sources driving both V minus and V plus. Now what do I mean by that? Let's take this previous problem and split. We have 4 sources. So in this, okay, the previous example has 4 independent sources. Let me actually call this V4. Okay, so consider V1 plus V1 and V2 and V3 together. That's easy enough to do. We've done that before. And then consider V4 alone. Now you could consider V1 by itself, V2 by itself, V3 by itself. That's fine. But since we've already worked the problem where we did V1, V2, and V3 all together using KCL, we already know that answer. That's going to be minus RF over R1 V1, RF over R2 V2 plus RF over R3 V3. We already know that. Now what we need to do is just add the superposed response due to V4. And what we have there is we have basically an inverting amplifier. We have RF, and then this resistor here that's going to go to ground because we turn V1, V2, V3 off is going to be a parallel combination of R1, R2, and R3. And here we have our input V4. Now if I gave you this problem by itself, you say, oh, this is just a non-inverting amplifier. I know the answer to that. We've derived that before. It's 1 plus RF over, let me call this R123, over R123, where R123 is the parallel combination of the 3 resistors and this all times V4. So just like that, we've been able to write the contribution due to V4, and so the complete contribution, or the complete response, complete V out response, not meaning complete as in transient and steady state, but I mean the response due to all of the independent sources working is simply VO is equal to 1 plus RF over R123 times V4, which is 2 volts in this case, minus RF over R1 V1 plus RF over R2 V2 plus RF over R3 V3. And see, this can be written almost by inspection. I would take this technique over going back and solving this right here. This, okay, avoid this. Avoid solving if possible, and usually it is possible. And so how do we avoid it in this case? Well, we turned off V4, so we set the 2 volts to 0, looked at the response due to just V1, 2, and 3, and then we turned V1, 2, and 3 off and looked only at the response due to V4. And that way we kind of keep it in this very simple inverting amplifier form and non-inverting amplifier form. All right, the next point is when solving for V+, ignore the op amp if there is no positive feedback to V+. Now, what do I mean by that? Let's go back to one of the circuits that we've seen before. Let's say, well, let's say we have this circuit here, R2, R1, call this V1, and now I have, let's say here, say V2, and V3, and so this R3, R4. Okay. Let's call this R2 and we'll call this RF. Okay. So how I would solve this is I look at this and I say, all right, this is a non-inverting, well, no. Depends on the vantage point. I was going to say non-inverting amplifier. From the vantage point of V1, okay, V1 sees an inverting amp topology, right? V2 and V3 see a non-inverting amp. And so what you need to find out along the way here is if it's a non-inverting amplifier, then you're applying the voltage, some external voltage to the non-inverting input right here. Right? So you need to know what this voltage is at the positive terminal, call it V+. Right? So to find V+, we can ignore the op amp. In other words, the op amp has no bearing on what V+ is going to be because there's no current flowing into this terminal. So all we have is two voltage sources, V2 and V3, and this is our voltage V+, and we can simply write that as a voltage division expression, R2 over R2 plus R3. I think I wrote this backwards. Yes, I did. R2 and R3. Okay, times V3 plus R3 over R2 plus R3 V2. And that's how we find V+. So in other words, what we've done is in finding V+, we can ignore the op amp. In this case, because there is no positive feedback to V+. Now, what would positive feedback look like? So we'll go positive feedback. Well, if we had something like this, which we haven't encountered these kind of problems yet, but let's say I had some voltage V2 here, and R2, and now let's say I tied a resistor back to the output, RP, I'll say, right? Now, V plus is equal to the superposition of two voltages, but one of them is V out. So I'm not ignoring the op amp per se. I mean, in a way I am, but I'm including the fact that the output voltage of the op amp is going to affect V plus. So we would have RP over RP plus R2 V2 plus R2 over RP plus R2 VO. All right. Now we're not solving this kind of problem right now, but I just wanted to identify how you would spot positive feedback. Positive feedback is indicated by a resistor going from, or some element going from the output voltage back to the positive terminal of positive input of the op amp. The next one, which one are we on? What number are we on? Number 5 is look for inverting and non-inverting amplifier forms. Okay, so let's take the problem that we had previously. RF and R1 with an input V1, and then we had let's see, we had R2, V2, and V3 and R3, and we want to solve for V out. So what I recognize here, as I mentioned on the last page, from the standpoint of V1, V1 quote-unquote sees an inverting amplifier. V2 and V3 quote-unquote see a non-inverting amplifier. And you might say, well, how do they see that? Well, V1 is connected into the inverting pin of the op amp through R1, but nevertheless connected to the inverting input. And so it is therefore part of an inverting amplifier, or it's going to, in its path is an inverting amplifier stage. Whereas V2 and V3 are connected through their respective resistors to the non-inverting input, V plus, of the op amp, and so there is a non-inverting amplifier in their path. So I would split this as into two circuits. I recognize an inverting topology like this, and here I have, if I turn both of my sources off, right, I have R2 and R3, V1, I'll call it VO prime, or VO1. Okay, this is equal to this where the non-inverting input is grounded, right? Because there's no current flowing into either input of my op amp, therefore the presence of R2 and R3 have no effect on the voltage V plus, right? Because there's no current flowing, so I might as well take them out. So I can write by inspection that I have VO1 is equal to minus RF over R1 V1. And I'm done with that. Now I'm going to write plus, because this whole circuit on the left is equal to this inverting stage, okay, and plus a non-inverting stage. And all I'm doing here is superposition. Okay. For the non-inverting stage, I have V1 turned off, so that goes to ground. And I can either treat V1, V2, and V3 separately. Oh, let's go ahead. I mean, in the end, I wouldn't have to. I'm sure you would not either. But let's just to take baby steps here. Let's treat them independently. So we'll say V2. And here we have V3 is off, Right, so we'll call this VO2. And what do we have? We have a non-inverting amplifier, so the gain is 1 plus RF over R1 times V plus, right, the voltage at the non-inverting input. But what is that voltage? That voltage is a voltage division of V2. It's R3 over R3 plus R2 times V2. And now we can consider our final input, where we have R2 grounded, and we have R3 tied to V3. And so our contribution from V3 is again 1 plus RF over R1. That does not change, times V plus. The only difference is that V plus is now R2 over R2 plus R3 times V3. So we can write the final result. VO is equal to VO1 plus VO2 plus VO3, which is equal to minus RF over R1 V1 plus 1 plus RF over R1 times, and we could write it as R3 V2 plus R2 V3 all over R2 plus R3. And so we have a term in V1, and let's split this out into two separate terms here. We have a term in V2 and then a term in V3. All right, so we've been able to do this almost all by inspection, by recognizing in this circuit that there's an inverting architecture and a non-inverting amplifier architecture, and we leverage off of the fact that we know that the inverting architecture has a gain of minus R feedback over R1, and the non-inverting has a gain of 1 plus R feedback over R1. Okay, number 6 we've talked about already, but I'll mention it again. Ignore op-amp loading. Now, you don't always do this, but when we're talking about this ideal analysis, we will do this. Ignore op-amp loading. So, for instance, here we have our inverting amplifier, and let's say that you have some other resistor R3 here connected between VO and ground. Yeah, I think I already talked about this, didn't I? I did. So I won't belabor this. Solve by ignoring R3. All right. So this is going to be just like V out will be the same as if you never had an R3. Okay, so if you see something like, for instance, an op-amp here that, say 2 op-amps tied together, right? And this is VO1, this is VO2, and there's some resistance Rx between them. When you look at this, you don't need to, when you solve for the output VO1, you don't need to be thinking about VO2. Unless somehow VO2 is going over and messing with the inputs of the first op-amp, you can ignore it. So you can find VO1 by itself, and you find VO2 by itself, and then, because those ultimately are just voltage sources, right? And, then maybe the question is, what's the current IRX, the current flowing through this resistor? Well, you'd find VO1 first, VO2, and then calculate the current. But you could solve these independently. You wouldn't need to look at both op-amps together. All right, the last one is consider Thevenizing the source or sources driving either op-amp input. So as an example, we have an inverting op-amp topology, and let's say that we have R1, V1, and we have a R2, say going to 1 volt here. Okay. The question is, what is VO? Or maybe the question is, if V1 varies by plus and minus 1 volt, by how much does VO vary? So what I'm looking for is, I know by now that VO is going to be some function of V1 and some function of the 1 volt. Right? And when I mean function here, it's going to be a constant. Right? So if I could replace all of this with some Thevenin equivalent, where I would have R Thev and V Thev here, and that goes into my inverting input, okay, then I would write VO is equal to minus, I can write this by inspection now, minus RF over R Thev times V Thev. Now I don't know what V Thev is. V Thev is going to be some weighted combination of V1 and the 1 volt. But I can immediately find what the Thevenin resistance is, because if I just turn off both of my sources and look in, I see that R1 is in parallel with R2. Right? And then I could also find V Thev if I wanted to, and that's just going to be a superposition of, using voltage division, of the two inputs. Right, so right now I can write by inspection, finally, VO is minus RF over R1 in parallel with R2 times, it's going to be this stuff here. Right? But all I'm interested in is the portion due to V1. Right, so I'm looking for this piece right here. And there we go. So you could simplify this. Let's see. In this case, we're going to have R1 in parallel with R2 is going to be R1, R2. Maybe this was not necessary after all. Maybe this wasn't a good example. So this would cross out. I'm going to get RF over R1. Yeah, this was not such a good example. But it brings up a good point. Yeah, this is a good plus. Plus this other part for the 1 volt. Okay, RF over R1 V1. Okay, I think this is going to end up being, it is going to be RF over R2 times 1 volt. Yeah, sorry, not a good example here. In fact, why does it work this way? Think of this is an interesting point here. Think about this circuit here. If I have R1, RF, and if my non-inverting input is grounded, then this voltage V minus is at 0 volts, right? Because it's equal to V plus. So because it's 0 volts, if I actually hang a resistor, this would be a good trick question to ask on a test. If I said Rx right here is equal to infinity, find VO, right? And you'd say, oh, VO is minus RF over R1 V1. And then I said, oh, what if Rx is equal to 1 microohm? Then what's VO equal to? And this is kind of strange, but if you truly have an ideal op-amp with infinite gain, because V minus is equal to V plus and is 0, with no voltage across that resistor Rx, there will be no current flowing through it. And so adding any value of Rx to ground from that node will not affect KCL at that node at all. And so it would still remain R minus RF over R1 times V1. Now in a real op-amp, where the gain AV is not infinite, but it's something large, like 10 to the 5 or so, a small enough RX would affect things. All right, so maybe this last point, there are cases where you do want to consider Thevenizing. The example I gave you here was not the best one, but maybe you'll come across that in your homework as you work through it.